So this video is going to discuss some hints on how to do the Prelab for the free body diagram experiment. I'm only going to talk about how to do question 1, that is the first case, this one that you're looking at, the cart on the track that's being accelerated by a hanger. I'm not going to give you any hints on doing question 2, so if you're stuck on that, get in touch with your lab instructor and they can give you a hand in person. Now, the first thing that students find confusing when they're trying to do this one is they often will create a free body diagram for the cart on the track, and they'll make a second free body diagram for the hanging mass, which you're supposed to do, and they forget that the mass of these two things is different. So be very careful to make sure that you distinguish between the mass of the cart and the mass of the hanger. So I've used a capital M for the cart and a small m for the hanger. So now let's create free body diagrams for these two objects. So that's what I've done here and here, just on top of the original diagram. The cart has 3 forces acting on it, so it's got the normal force pointed upward and the weight of the cart, mg, pointed downward, and it's also got the tension force due to this string. Now, we only really care about finding the acceleration, so we don't actually need to do this y direction analysis, but I'll do it anyway just for the sake of completeness. We always start by saying the mass times the acceleration equals the sum of the forces, so F equals ma. And you say mass times acceleration is going to be equal to the sum of all the forces on the cart. So right now we're just talking about the y direction. The acceleration up and down is 0. It's not moving up or down. So we've got mass times 0 acceleration gives us 0. And then we sum up the forces, and there's only 2 forces in the y direction. There's the normal force and the weight of the cart. Normal force points up, so I put it down as positive, and the weight of the cart points down, so I put it as negative. So n minus w equals 0. And obviously we get to rearrange that to find that the normal force, the magnitude of it, equals the magnitude of the weight of the cart. Like I said, we don't actually need to do this to do the experiment. So let's look at the x direction now. So again, we start the same way. Mass times acceleration is going to be equal to the sum of all the forces on the cart in the x direction. So mass times acceleration equals, and there is only one force in the x direction, that's the tension on the string. So it's simply ma equals t for the cart. So now we come over here and we do a similar analysis for the hanging mass. So again, we start with mass times acceleration equals the sum of the forces. And we're just careful to remember that the mass here is small m, not big M, so it's a different mass than for the cart. There are 2 forces on here. There's the tension in the string and the weight of the hanger. Keep in mind that these 2 forces are not balanced. This hanger is accelerating, so don't say that tension equals the weight. That's not true in this case. If it was stationary or moving at a constant velocity, you could say that, but we are actually accelerating, so these 2 things are not equal to each other. So mass times acceleration equals the sum of the forces. So mass times acceleration equals, and here you have to be a little bit careful with your minus signs. So what I've done is I have defined the direction of the acceleration to be my positive direction. And if A is pointing in the positive direction, that means that the weight, that force, is a positive force. So mg for the weight of the hanger is a positive quantity. And tension, which is pointing in the opposite direction to the acceleration, which is my positive direction, must be a negative value. So I've got mass times acceleration, and I'm assuming implicitly that A is the positive direction. Mass times acceleration equals mg, that's the weight of the hanger, minus the tension. So the tension is put down as negative just because it's going in the opposite direction of A. So that's the other thing that students tend to get wrong on this, is that they mess up a minus sign in here. So now we're ready to solve for the acceleration. And we've got a problem. We want to use this equation, but there's 2 unknowns. There's the acceleration, which we want. There's also tension. We don't experimentally measure the tension on the string. So how do we get rid of tension in order to be able to solve for the acceleration? Well, down here you have another equation that has tension in it, and everything on this side of the equation is something we're allowed to put in here. So A is unknown, but that's okay. We want to solve for that. And we measure the mass of the cart. So you take this equation and you substitute it in here to get rid of the tension. And then you've got an equation where you've got one unknown, the acceleration. You've got two different masses, but only one unknown, which is the thing you want to solve for. So you substitute this into here, and then you solve for A, and then you should be able to complete your pre-lab.